Alright, in this lab we showed the relationship between omega, which is how fast the angle changes in circular momentum, which is change in theta over change in time, and velocity, and the radius using math and actual trials. With this relation between velocity and the centripetal acceleration, we deduced that v squared divided by r is equal to the centripetal acceleration. Also, we recognize that a normal and a tangential, which is the acceleration upward caused by the turntable, and the acceleration tangential, which is what this feels when it spins around, are both constant. So here we have a record turntable, and we have an accelerometer attached to it. And this accelerometer, as you can see, this section of the wire is pointed directly at the center of the turntable. Now we measured the radius of the turntable, which is 12.5 centimeters, is that right? Mm-hmm. Alright, so this will measure both, or all x, y, and z directions. In this case, the x direction will be the centripetal acceleration, which is what it feels trying to get to the center of the radius as it spins. The y direction, which is tangential acceleration, which is what it constantly feels at pulling it toward the side as it spins. And the z direction, which is normal acceleration, which is what it feels just by the turntable holding it up. So let's get a good view there. And we're trying to do our best to make sure that the wires don't get tangled up as we spin. Alright, so here we have our lab setup. We have the turntable, which we're going to spin at 33 1/3 revolutions per minute, 45, and then 78. We have the accelerometer on the turntable.
Complete V level.
Mm-hmm. And set to record the exact, well, as exactly as we can make it, all three accelerations. This is connected to the LabQuest device, which will record what the accelerometer shows and the accelerations it feels. That is connected to our laptop. We are using the program Logger Pro to make a graphical representation of what the accelerometer feels. Alright, I think we're ready to start.
Okay.
Alright, so we're going to start off at 33 miles per hour.
Revolutions per minute.
Exactly.
Do you want to hit collect, Dan?
I will. Fine. Here we go. So now we're going at 33 RPM. Now 45.
Okay.
And now 78 revolutions.
Okay. We're done.
Yoinks!
And we finished collecting our data.
Alright, so for the turntable experiment, we start out with three speeds in terms of RPM. The first one, we had a speed of 33 1/3 RPM. Now, once we calculated that out and converted it to meters per second, because the radius was 12, we then calculated our velocity in meters per second to be 0.42 meters per second. From there, we just squared it, which means that v squared equals 0.18 meters. Oh, by the way, this is 0.12 meters. It's 12 centimeters. And so when we divide v squared by r, which will give us the centripetal acceleration, it ended up being 1.5 meters per second squared. On your graph, you'll see that for the first plateau at 33 1/3 RPM, our median was negative 1.3 meters per second squared, which is pretty darn close. And it's negative only because it was going in the opposite direction. So if we go back to our calculations, our next velocity was 45 RPM. And again, the radius will always be 0.12 meters. And so if we calculate out into meters per second, we get that it was about 0.57 meters per second. And again, we squared that, which gave us 0.32, and divide that by our radius, and we get that the centripetal acceleration this time was 2.7 meters per second squared. And again, if we look on our graph, we have the second plateau right about here. And as you can see, our centripetal acceleration was about 2.6, which is, again, even closer. And so that only proves that our calculations, again, worked. And for the final velocity was 78 RPM. We calculated that out to be 0.98 meters per second. Squared it. That gave us 0.96. And put that over our radius of 0.12. And that gave us a centripetal acceleration of 8 meters per second squared. And if we go back to our graph, we see that the mean for our third plateau, although it is very tiny, is negative 9.08, which is not as close, but still close enough. And so therefore we have determined that our accelerometer setup was in accordance with the actual calculations of centripetal acceleration.